Alright, gentlemen, so today we're going to be looking at section 7.5, which deals with multiplying um, expressions containing radicals. So I know that you have some experience with multiplying with radicals, so our focus primarily today will be how to use the idea of multiplying with radicals to do what's called rationalizing the denominator. And what that means is to get rid of any radicals that are in the denominator of a fraction. We never want to leave an answer with a radical in the denominator of a fraction, um, simply because we can't have an irrational number of parts or a non-terminating decimal number of parts. So we want to make sure that our denominator is a whole number. All right, and we're going to be using a couple different techniques in order to do that. It will depend on whether your denominator is a monomial or a binomial. And we'll talk about both of those techniques. So we'll look at rationalizing the denominator. You'll have an opportunity to add some notes to what you started on homework 23. So you should have homework 23 out as you're going to be adding some examples to the end of those self-checks from section 7.5, much like you did with yesterday's questions that you added to the end of the self-checks from section 7.4. So at this time, if you don't have the section 7.5 self-checks out from homework 23, go ahead and pause the video, take out that homework assignment along with a pencil, and then you can come back and proceed from there. So as we said, rationalizing the denominator means that you want to eliminate any radicals in the denominator of a fraction. Right? The way that we're going to do this is to multiply your fraction by a variation of 1, but we're going to choose a variation of 1 that will make the denominator equal a whole number. Right? And so what we mean by a variation of 1 is we need to multiply the numerator of our fraction by the same thing as we multiply the denominator by, so as to not change the value of your fraction. All right, so this is where having an understanding of the perfect squares and perfect cubes is going to come in handy. Because if I look at an example like number 1, where I have the square root of 2 in the denominator, I have to try to find the smallest perfect square that the square root of 2 divides into evenly. So if I start going through my list of perfect squares, I know that 4 is the smallest perfect square that the square root of 2 will divide into. And so what I'm going to do is I'm going to choose to multiply the denominator by some value that's going to make the denominator equal to the square root of 4. And as long as I multiply the numerator by that same value, I won't change the value of my fraction. All right, so the value that I'm going to choose to multiply here is root 2, because root 2 times root 2 is root 4, and that would make my denominator now a simplifiable radical. So if I take my original fraction and I multiply it by my variation of 1, root 2 over root 2, what that does again is make my denominator a perfect square, square root of 4, so that I can simplify and no longer have a radical in the denominator. All right, so it is okay to have a radical in the numerator, but we do not want to have a radical in the denominator. All right, so we have officially then rationalized this denominator. All right, common mistake with this concept, particularly with squares, is to think that you must multiply the radical by itself. That's not necessarily the case. All right, it will work if you always multiply a square root by itself, but it's not necessarily going to be the most efficient way. Right, you want to always find the smallest perfect square that your radical divides into, and then multiply to get that smallest perfect square in the denominator. All right, so to illustrate that idea further, we'll take a look at something with a cube root in the denominator, like example 2. In this case, we cannot multiply by the cube root of 4 over the cube root of 4, because that would make my denominator the cube root of 16, which is not a perfect cube. All right, so again, when I'm trying to rationalize the denominator here, what I would like to do is to find the smallest perfect cube that the cube root of 4 divides into evenly. So if I start going through my list of perfect cubes, the cube root of 8 is the smallest perfect cube that the cube root of 4 divides into evenly. And so to rationalize the denominator here, I'm going to take my original fraction and I'm going to multiply by a variation of 1 that makes my denominator a perfect cube. That happens to be the cube root of 2. And again, as long as I multiply the numerator by the same thing as the denominator, I don't change the value of my fraction. When I actually do the multiplying, I end up with 5 times the cube root of 2 over the cube root of 8 in the denominator. And then I can simplify the cube root of 8 to be just 2. And now I have officially rationalized my denominator because I no longer have a radical in that denominator. So at this point in time, I want you to take a moment and to try a couple of examples. I want you to add these on after the self-checks from section 7.5. And again, when I collect this assignment from you next week, I'll be looking to see that all of the in-class examples for today have been added to the self-checks you started on homework 23. Take a moment, pause the video, complete numbers 56 and 60 here, where you're going to rationalize the denominator, and then you can come back and check your solutions once you have completed both questions. So with number 56, where we started with the cube root of 3 over the cube root of 50, again, I don't want to necessarily multiply the radical by itself. That's going to give me really big numbers that I'm going to have to simplify further and eventually end up with the same answer, but it's just going to be a much more painstaking process to get there. What I want to do is try to figure out what is the smallest perfect square that the square root of 50 divides into evenly. So if I start going through my list of perfect squares, clearly anything less than 50 is not going to work because 50 won't divide into it evenly. So if I start looking at numbers bigger than 50, 100 is the smallest perfect square that the square root of 50 would divide into evenly. So I can make my denominator the square root of 100 by taking my original expression, multiplying both the numerator and denominator by root 2 over root 2. That gives me a perfect square in the denominator, which I can simplify to be just a whole number 10. All right, the multiplying in the numerator just happens to be a consequence, so I end up with a radical in the numerator by chance here, which is fine. Again, the objective is to rationalize the denominator, so I have now gotten rid of that radical from my denominator. With number 60, again, we want to look at what is the smallest perfect cube that the cube root of 6 divides into. So if I start going through my list of perfect cubes, 6 does not divide into 8, 27, 64, or 125 evenly. However, it does divide into 216 evenly. So if I take my original radical, 2 over the cube root of 6, and I multiply that by the cube root of 36 over the cube root of 36, what that does is that gives me a denominator that is the cube root of 216, which again is a perfect cube that is equal to 6. And so I'm then able to rationalize my denominator by multiplying both the numerator and denominator by the cube root of 36. But once I've gotten rid of the radical in the denominator, I want to simplify my fraction as much as possible. And I'm going to simplify by reducing the whole numbers. Think of this fraction as 2 over 6, one fraction, times the cube root of 36 over 1, a separate fraction. Right? 2 over 6 we can reduce to 1 over 3. And the cube root of 36 is already in its simplest form. I know that because no perfect cubes divide into 36 evenly. So when I reduce my fraction 2 over 6 to 1/3, and I multiply that by the cube root of 36 over 1, I end up with a final answer in simplest form of the cube root of 36 over 3. So we've talked about rationalizing the denominator with a monomial term in the denominator. If there's a binomial term in the denominator, it's a little different. The objective is still the same. We're still trying to eliminate the radical in the denominator, but the way that we're going to eliminate that radical is a little different. When you have a binomial term, as in example 3 in the denominator, you need to multiply by what's called its conjugate. Right? You've been dealing with multiplying conjugates for quite some time now. You just haven't necessarily used that term conjugate. Think multiplying expressions that have the same terms with different signs between them. We talked about this in chapter 5. When we multiply two binomials that have the same terms with different signs between them, the result is the difference of two perfect squares. Think something like x plus 2 times x minus 2. You end up with a product that is the difference of two squares. And so we're going to use that same idea to eliminate the radical from this denominator. So I'm still going to multiply the numerator and denominator by the same value so that I don't change the value of my fraction. But this time I'm going to have to use the conjugate of the denominator. So if root 2 plus 1 is my original denominator, its conjugate is going to have the same terms, root 2 and 1, but with a different sign between it. So the conjugate for root 2 plus 1 is root 2 minus 1. And again, as long as I multiply the denominator and numerator by the same value, I'm going to end up with an equivalent fraction, a fraction that's equivalent to my original. All right, so the multiplying here in the numerator is just distributing. 3 times root 2 and 3 times negative 1. No problem. And the denominator is going to require that we FOIL because we have one binomial times another. So when I start to do that work, in the numerator, I'm going to end up with 3 root 2 minus 3. Simplest form, I'm pretty much done with that numerator. In the denominator, my first times my first is root 2 times root 2, or root 2 squared. Then my outer times my outer is negative 1 times root 2, which is negative root 2. My inner times my inner is positive 1 times root 2, which is positive 1 root 2. And my last times my last is positive 1 times negative 1, which is negative 1. And so when I go through and I do all the simplifying, I'm going to end up with 2. The outer and inner terms cancel each other out, and then minus 1. So 2 minus 1 becomes my denominator when I FOIL those conjugates. And when I simplify those, I can essentially eliminate the denominator because it's just 1, and I come up with my final answer, 3 root 2 minus 3. So again, when we're rationalizing the denominator with a fraction with a binomial in its denominator, we have to multiply both numerator and denominator by the conjugate of the original denominator. For the last example today, I want you to, again, take out your self-checks from section 7.5 and add this third example after those self-checks. This example is number 70, and I want you to rationalize this denominator with a binomial. And so this would be a good time for you to pause the video, complete question number 70, and then return to the video after you've completed number 70. So when we take our original fraction, to rationalize that denominator, we're going to multiply by its conjugate. The conjugate for root 3 minus 2 would be root 3 plus 2. And again, I'm going to have to multiply the numerator by the same thing. So this is my variation of 1, root 3 plus 2 over root 3 plus 2. In the numerator, it's going to require that I distribute. Root 3 times root 3 is 3, and root 3 times positive 2 is positive 2 root 3. In the denominator, I'm going to have to FOIL. Root 3 times root 3 is 3. Root 3 times positive 2 is positive 2 root 3. Negative 2 times root 3 is negative 2 root 3. And then negative 2 times negative 2 is negative 4. And because I used conjugates in the denominator, the outer and inner terms will cancel each other out, and I'll be left with a denominator that is 3 minus 4, or negative 1. And of course, we can't leave any fraction with a negative number in its denominator. That's not its simplest form. So we're going to simplify that further by splitting the numerator, or splitting this one fraction into two separate fractions. We'll make it 3 over negative 1 plus 2 root 3 over negative 1, and simplify those both to be negative 3 and minus 2 root 3 as my final answer. So with these three examples added to the self-checks on section 7.5, coupled with the reading you did from section 7.5, you should be able to complete tonight's homework, which is homework assignment number 25. So you have the duration of the class period today to work on completing homework number 25. and hopefully won't take you too much additional time outside of class to complete this assignment tonight. Have a great day, gentlemen. See you soon. Go Bells.